Distributive Properties of Cartesian Products. Welcome, everyone. Before we dive into today's new topic, let's take a quick moment to reflect on what we have already covered. In our previous lessons, we mastered the fundamentals of finding the Cartesian product of two sets, essentially, how to pair elements from one set with elements from another. Today, we are going to take that knowledge a step further. We are going to explore how the Cartesian product interacts with other fundamental set operations, specifically the union and the intersection. Now, you might be wondering what interacts means in this context. To understand this, we need to look at a concept called the distributive property. In mathematics, a distributive property occurs when an operation can be applied to each individual element inside a set of parentheses. To make this clearer, think back to your basic algebra classes. You are already very familiar with this rule. A multiplied by the quantity b plus c equals a b plus a c. You see how the is distributed to both the b and the c. Well, today's lesson follows that exact same logic. We are going to demonstrate that, similarly, the Cartesian product distributes over both the union and the intersection of sets. Over the next few slides, we will prove this mathematically and even look at a real-world example to see it in action. Distribution over intersection. Now that we understand what a distributive property is in algebra, let's apply that same logic to set theory. Our first specific property focuses on the intersection. This property tells us that if you take the Cartesian product of set A with the intersection of sets B and C, the result is exactly the same as finding the intersection of two separate Cartesian products. Specifically, the product of A and B intersected with the product of A and C. In mathematical notation, we write this as across open parenthesis B intersection C close parenthesis equals open parenthesis across B close parenthesis intersection open parenthesis across C close parenthesis. To make sure this isn't just an abstract rule, let's actually verify it with a concrete example. We will use these three sets. Set A contains the elements 1 and 2, set B contains the elements x and y, and set C contains the elements y and z. We'll use these in the next few slides to work through the left-hand side and the right-hand side step by step. Step-by-step example for intersection. Now that we have established the mathematical statement for the distributive property over intersection, let's move into the practical verification. On this slide, we will begin step 1, where our goal is to solve the left-hand side of our equation, which is a cross-parenthesized B intersection C. To do this correctly, we must follow the order of operations, starting inside the parentheses. First, we need to find the intersection of set B and set C. Looking back at the sets we defined on the previous slide, we can see that the intersection of B and C results in a set containing only y, because y is the only common element shared by both sets. Once we have that result, we can proceed to the next part of the left-hand side. We now find the Cartesian product of set A and our new intersection set. This means we take set A, which contains 1 and 2, and pair them with our set containing only y. This gives us our final result for the left-hand side. A set containing the ordered pair 1, y and the ordered pair 2, y. Keep these results in mind, because in the next slide, we will calculate the right-hand side to see if they match. Step-by-step example for intersection, continued. Now that we have successfully calculated the left-hand side in the previous step, let's move on to step 2, where we solve the right-hand side of our equation. Remember, our goal here is to find the intersection of two different Cartesian products, a times B intersected with a times C. First, let's calculate the Cartesian product of A and B using the sets we defined earlier, A equals 1 and 2, and B equals x and y. We pair every element from A with every element from B. This gives us the set containing the ordered pairs 1x, 1y, 2x, and 2y. Next, we need to find the Cartesian product of A and C here. C contains y and z, so we pair our elements from A with those from C, resulting in the set 1y, 1z, 2y, and 2z. Finally, to complete the right-hand side, we look for the intersection of these two new sets we just created. We are looking for the ordered pairs that appear in both lists. If you look closely, you'll see that the pairs 1y and 2y are present in both results. Therefore, the intersection of a times b and a times c equals the set containing 1y and 2y. As we will see in the next slide, this result perfectly matches what we found in step 1. Conclusion for intersection. Now, let's take a look at what we have achieved. If you look back at our calculations from the previous 2 slides, you will see that our result for the left-hand side, which was the set containing the ordered pairs 1y and 2y, is exactly identical to the result we obtained for the right-hand side, which was also the set containing 1y and 2y, because these two sets are perfectly equal. We have successfully verified the distributive property. This confirms that across the intersection of B and C is indeed equal to the intersection of across B and across C. Distribution over union. The second distributive property states that when you take the Cartesian product of a set A and the union of two other sets, B and C, the result is exactly the same as finding the union of two separate Cartesian products, a times B and a times C. In mathematical terms, we write this as across open parenthesis B union C close parenthesis equals open parenthesis across B close parenthesis union open parenthesis across C close parenthesis. To make this concept a bit more intuitive and less abstract than the previous example, let's step away from numbers and letters and imagine you are designing an outfit. Suppose you have 3 different sets of clothing. Set A represents your choice of shirts, specifically a white shirt and a blue shirt. Set B represents your choice of formal pants, which is just black pants. And finally, Set C represents your choice of casual pants, which is just jeans. We are going to use these sets in the next few slides to see how this property works in a real-world scenario. Now that we have successfully verified how the Cartesian product distributes over an intersection, let's move on to our second property, distribution over a union. Real-world example for union. Now that we have the sets for our shirts and pants, let's apply the distributive property to see it in action. Our goal here is to find every possible outfit combination you could make by pairing one shirt with any type of pants, whether that's formal or casual. To prove the property works, we'll start with step 1, where we solve the left-hand side of our equation, which is across the quantity B union C. First, we need to look inside the parentheses and perform the union operation on our pants. We take set B, which is black pants, and combine it with set C, which is jeans. This gives us a new, larger set for our pants. B union C equals the set containing black pants and jeans. Now we take our set of shirts, A, and find the Cartesian product with this new set of pants. This means we pair every single shirt with every single type of pants available. When we calculate across B union C, we get a list of 4 possible outfits: white shirt with black pants, white shirt with jeans, blue shirt with black pants, and finally, blue shirt with jeans. Keep this list in mind, because in the next slide, we are going to see if calculating the products separately and then joining them gives us this exact same result. Real-world example for union, continued. Now that we have calculated the left-hand side in the previous slide, let's move on to step 2, where we solve the right-hand side of our equation. Specifically, we are looking at the expression, the Cartesian product of set A with set B, union, the Cartesian product of set A with set C. First, let's find all the possible combinations of our shirts and formal pants. By calculating a times B, we get a set containing 2 pairs, white shirt with black pants and blue shirt with black pants. Next, we do the same for our casual options. When we find the Cartesian product of A and C, we get the pairs, white shirt with jeans and blue shirt with jeans. Finally, to complete the right-hand side, we need to perform the union operation. This means we are going to combine both of these sets of combinations into one single, large set. When we take the union of these 2 groups, we end up with our full list of 4 possible outfits: white shirt with black pants, blue shirt with black pants, white shirt with jeans, and blue shirt with jeans. As you can see, this result is exactly what we calculated in the previous step, which brings us to our conclusion in the next slide. Conclusion for union. Now, let's take a look at what we've just accomplished. If you compare the results from our two steps, you'll notice that the final list of outfit combinations we calculated on the left-hand side is exactly the same as the list we compiled on the right-hand side. Because these two sets of pairs are identical, we have successfully proven the second distributive property. In mathematical terms, we can conclude that across B union C equals across B. Union across C, this confirms that the Cartesian product distributes over the union of sets, just as we predicted at the start of this example. Common mistakes to avoid. Now that we have seen how the distributive property works for both intersection and union, I want to pause and highlight some common pitfalls. As you move forward with more complex set theory problems, keep these 3 points in mind to avoid losing marks. First, be very careful not to confuse the union and intersection symbols. It is a very common mistake to swap the U-shaped symbol for the N-shaped symbol. Just remember, the union symbol, which looks like a U, represents all elements from both sets, effectively expanding your results. On the other hand, the intersection symbol, which looks like an upside-down U, only looks for common elements, which narrows your results down. Second, pay close attention to the order of your pairs. When you are calculating something like across B, union, across C, you must ensure that the first element in every single ordered pair always comes from set A. A frequent error I see is students accidentally swapping the elements, writing B, A instead of a B. In Cartesian products, order is everything. Finally, do not assume commutativity. In basic addition, the order doesn't matter, but in Cartesian products, A cross B is not equal to B cross A. This is crucial for the distributive property we just studied. The property only holds true if set A remains in that same first position on both sides of the equation. Keep these tips in mind as we wrap up our lesson with a quick summary of the key takeaways. Key takeaways. All right, we have reached the end of our lesson. Let's wrap everything up by reviewing the key takeaways so you can feel confident with these properties. First, let's look at the distributive law for intersection. As we demonstrated through our step-by-step calculation earlier, the formula is across, the intersection of B and C equals across B, intersected with across C in simpler terms. What this tells us is that the product of an intersection is exactly the same as the intersection of the individual products. Next, we have the distributive law for union. Just like our outfit example with the shirts and pants, the formula is across, the union of B and C equals across B. Unioned with across C, this means that the product of a union is equal to the union of the products. Finally, I want you to notice the consistency between these two rules. In both properties, you can think of set A as acting like a constant multiplier. Just like the number, A in algebra, set A is being distributed across the other two sets, whether we are dealing with an intersection or a union. As long as you keep this pattern in mind and avoid the common mistakes we discussed, you'll master this topic in no time. Great job today!